In this lesson, we are going to learn how to find power series for functions in a more general way than just using the geometric series or a derivative of something whose power series we obtained using a geometric series. Okay, so the first question is which functions have power series representations, and then how do we find these representations? This first question we're going to deal with in a later lesson because showing that's a teensy bit complicated. So we're just going to talk about how do we find them, assuming that your function f has a power series representation. So the first thing we're going to do is we're going to suppose that f is a function that can be represented by a power series. Okay, so if we know f is a function that can be represented by a power series, then what we have is that f of x is equal to some constant c0 plus c1 times x minus a plus c2 x minus a squared plus c3 x minus a to the third, etc. And just notice that we did not assume that this power series was centered at 0. We have this thing is centered at x equals a. And what we're going to try to figure out is how do these coefficients, those c's, relate to the original function f, if at all. So the question we're asking, how do the c sub n's relate to f? Okay, well the first thing to notice is that if you plug in a, this is 0, this is 0, this is 0, and everything, all that stuff is 0 except for c0. So f of a is going to equal c0. So whatever you get in your function when you plug in the point that you're centered around, that's that first coefficient. Now we're going to take a derivative, and that'll help us find the next ones. F prime of x, well c0 is a constant, its derivative is 0. The derivative of c1 times x minus a is just c1. Because you have c1x, that's derivative is c1, and then c1 times a is a constant, derivative is 0. Plus 2c2 x minus a squared plus 3c3 x minus a cubed, and plus just one more for kicks, 4c4 x minus a to the third. And I made a bit of a boo-boo. This should be x minus a squared, etc. Now we're going to use the same trick as before. Plug in a, f prime of a. Notice that this guy's 0, this guy's 0, this guy's 0. So f prime of a is c1. So whatever your function, its derivative evaluated at your center point gives you the coefficient of the x minus a term. And then repeat, f prime prime of x. Now c1's gone. Oh, and I made more than one mistake. That should have been c2 x minus a to the first. Okay, so we have 2c2 plus 3 times 2c3 x minus a plus 4 times 3 times c4 x minus a squared. There's a reason I'm not multiplying stuff together. It's because it's actually easier to see the pattern if you don't. And once again, you plug in 0. Well, f prime prime of a is equal to 2c2, which implies, solving for c2, that c2 is 1/2 f prime prime of a. And I think one more derivative and you're going to see the pattern. So the third derivative is equal to 3 times 2 times c3 plus 4 times 3 times 2 c4 x minus a plus more stuff, input a, and we get all the later stuff goes to 0, 3 3 times 2c3, which implies that c3 is 1 over 3 times 2 f prime 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 of a. And I'm going to write that 3 times 2 as 3 factorial. F prime prime of a over 3 factorial. Notice this one above is f prime prime a over 2 factorial. 2 factorial is just 2 times 1. And this is the same thing as f prime of a over 1 factorial, because 1 factorial is 1. And this is, instead of, well, no derivative is just the original function, f of a, think of it as the 0th derivative, as in none, over 0 factorial. Remember that 0 factorial, by definition, is equal to 1. So if you were asked to find the value of that fourth c, c sub 4 is going to equal the 4th derivative at a over 4 factorial. The 5th coefficient would be the 5th derivative at a over 5 factorial. And that gives us the following pattern. So if f has a power series representation at a, that is, f of x can be expressed in this form for all x minus a's less than some r, then those c sub n's are given by the nth derivative evaluated at a over n factorial. So if you're asked to find a power series representation, you're going to have to find a pattern for these. This is called the Taylor series of the function of f at or about or centered at the point A. In this lesson, we're going to focus on a special case of a equals 0, and that case is called a Maclaurin series. And in that case, this formula becomes, well, let's just write it in summation notation, then kind of list out what it is as well. So a sum from n equals 0 to infinity. So we have the nth derivative evaluated at 0 now over n factorial. Those are our coefficients. X minus a to the n becomes x to the n. And listing out these terms, which usually is the way to think about it, is to list the terms and look for a pattern. This is f of 0, technically over 0 factorial, but that's just 1. F prime of 1 over 1 factorial times x plus f prime prime of, that should be 0, f prime prime of 0 over 2 factorial x squared, f triple prime at 0 over 3 factorial x cubed, etc. So given a function, you need to find a pattern for what happens when you plug 0 into its derivatives. So find the Maclaurin series for the function f of x equals e to the x and its radius of convergence. Then give an expression for e as an infinite series. So the first thing you should do is find some derivatives. Okay, so we have f of x is e to the x, f prime of x is e to the x, second derivative is e to the x, etc. And so our Maclaurin series, and I'm just going to say e to the x is equal to this because we'll be able to prove later that it is equal to f of 0 plus f prime of 0 times x plus second derivative at 0 over 2 factorial x squared plus third derivative at 0 over 3 factorial x cubed, etc. When you input 0 into e to the x, e to the 0 is 1. The derivative is e to the x as well, so we'll have 1x, 1 over 2 factorial x squared, 1 over 3 factorial x to the third. Next would come 1 over 4 factorial x to the fourth. So in summation notation, this is a sum from n equals 0 to infinity. Okay, we obviously have x to the n, and then over n factorial. It's a really easy application of the ratio test, and I'm going to skip it actually. And that's going to show you that your radius of convergence is equal to infinity. Therefore, your interval of convergence is minus infinity to infinity, which means this series will converge no matter what you plug in for x. And kind of a cool thing you can do now, if you want to give an expression for e as an infinite series, e to the first is equal to this series with 1 plugged in for x, because 1's been plugged in for the x spot. So that's the sum from n equals 0 to infinity, 1 to the n over n factorial, or the sum from n equals 0 to infinity, 1 over n factorial. And the kind of neat thing about that is that now you could approximate e using a partial sum, as in plug in 0 up until, say, 20 or something in this formula, and do 1 over 0 factorial plus 1 over 1 factorial. So e is equal to 1 over 0 factorial, plus 1 over 1 factorial, plus 1 over 2 factorial, plus 1 over 3 factorial, etc. And these first two terms add to 2, so you can see the rest of this is giving the rest of the e. And I don't think it even takes very many terms to estimate this e to a reasonable degree of accuracy, and this might be how your calculator estimates e. Okay, another common function, let's find a Maclaurin series for sine. So the pattern for the derivatives isn't quite as easy here. Okay, so let's first of all, f of 0 is sine of 0, which is 0. F prime of 0, I'm finding derivatives and plugging in 0 at the same time just to save some space. So the derivative of sine is cosine. So f prime of 0 is cosine of 0, which is 1. And the second derivative, okay, cosine's derivative is negative sine. That's going to be 0 again. The third derivative will be negative cosine, which gives us negative 1. And the fourth derivative puts us back at sine of 0, which is 0. Okay, so sine of x is equal to f of 0, f prime of 0 times x, plus second derivative at 0 over 2 factorial x squared, third derivative at 0 over 3 factorial x cubed, etc. A lot of these terms are going to 0 out. The first term, f of 0, is 0. Then we have 1x. Then we have another 0 term. Next, f triple prime at 0 is negative 1, so negative x cubed over 3 factorial. The next term is going to be 0. Then we'll be at positive 1 again, so we'll have plus x to the 5th over 5 factorial. Next, you can get the pattern comes negative x to the 7th over 7 factorial, etc. Notice that we're only having odd powers. So this is x minus x cubed over 3 factorial, plus x to the 5th over 5 factorial, minus x to the 7th over 7 factorial, plus other stuff, which in a summation notation form, we're going to start our sum at 0 because most people do. Okay. Now, the way to get odd numbers is to either do 2n minus 1 or 2n plus 1. So to figure out which one to use. So 2n minus 1, if we begin our sum at n equals 0, will give us, when you input 0, gives us 1. When you input 1, gives us 3. So that's the proper thing to use. We'll have a negative 1 to the n, because we're flip-flopping, and that is the right power to have because our first term is positive, x to the 2n plus 1. And remember that sine is an odd function. Look, odd powers, which is kind of neat. And once again, you can use the ratio test to show that the radius of convergence r is infinity here. You don't have to do that, but it's not a very hard thing to do, and maybe at some point in time we'll make you do it. Okay, find the Maclaurin series for cosine. Well, here's a clever trick. You don't have to revert to the definition here. You could, and that's not going to be wrong. But the clever trick is to note that there's a relationship between sine and cosine. The derivative of sine is equal to cosine. So therefore, we can find cosine's power series by taking the derivative of sines. Well, and sine's power series was x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, etc., and more stuff. You differentiate this term by term and we get 1. X cubed will become 3x squared. So 3x squared over 3 factorial. 5x to the 4th over 5 factorial. 7x to the 6th over 7 factorial, plus more stuff. And notice that the 3 cancels the 3 factorial. So you have 1 minus x squared over 2 factorial, plus x to the 4th over 4 factorial, minus x to the 6th over 6 factorial. And where cosine's an even function, we have all the even powers. Also note that when you plug in 0 for x, cosine of 0 is 1. Same thing happens on this side. So here's that in summation notation. It's the sum from n equals 0 to infinity, negative 1 to the n, x to the 2n over the quantity 2n factorial. It has the same radius of convergence as sine. And that actually comes from our theorem that we have that says that if you take the derivative of a power series, the radius for convergence remains unchanged. It's only convergence at the endpoints that could change. Now, using those series that we've developed, you can find series for functions that are related, so products and quotients and stuff like that. You don't have to try to do derivatives and rederive stuff. So the power series for f of x, which is x squared times sine of x, you can find this by taking x squared times the power series for sine. And that power series was the sum from n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1, all over 2n plus 1 factorial. That becomes the sum from n equals 0 to infinity, negative 1 to the n, x to the 2n plus 3, moving the x squared in the sum and adding exponents, over 2n plus 1 factorial. So the moral of the story there is don't try to derive this by the definition. Use a series that you know. Same thing for this one. You see how we have x and then e to the something. Well, the series for e to the x is the sum from n equals 0 to infinity, x to the n over n factorial. Because we have e to the 3x, we just input 3x for that x. So the 3x, the quantity to the n over n factorial. And that's the same thing as the sum n equals 0 to infinity, 3 to the n, x to the n over n factorial, which is the sum from n equals 0 to infinity, 3 to the n, x to the n plus 1 over n factorial. Another common series is the binomial series, and we're going to find the Maclaurin for this. This comes up a lot in things like statistics. So it's just quite tricky the derivation is not very hard, it's just the application of it that's a little bit tricky. So we have a function of the form 1 plus x to the k power, where k is any real number. So I'm just going to tell you what the radius of convergence is because it's just kind of tedious to show it. So find some derivatives. So f of x is 1 plus x to the k. So therefore f of 0 is just 1 to the k, or 1. F prime of x, just use your power rule, is k 1 plus x to the k minus 1. So therefore f prime of 0 is k, because 1 to any power is still 1. The second derivative is k times k minus 1 1 plus x to the k minus 2, and the second derivative at 0 is k times k minus 1. I think you can see the pattern now. The third derivative at 0 is going to be k times k minus 1 times k minus 2. The fourth derivative at 0 is going to be k minus 1, k minus 2, k minus 3. And in general, the nth derivative, that'll be k minus 1, k minus 2, all the way down to, I just need a terminal point. K minus n, is that correct? Well, this was the fourth derivative, this was k minus 3. So the way you account for that is this could be thought of as k minus 4 plus 1. Then the minus 4 plus 1 makes minus 3. So you need a plus 1 there. All right, and then our general form for our Maclaurin series, our f of x, is a sum from n equals 0 to infinity, k minus 1, blah, 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 k minus n plus 1 over n factorial times x to the n, which can be simplified into this other this notation your book uses called choose notation. This is called k choose n. K choose n. And it's equal to k factorial over n factorial and k minus n factorial. And really, we're not going to use that much. So we had k factorial over n factorial and minus k. What really is helpful is this sort of pattern that we found here. Because this factorial thing only works if you have integers, and we're often going to have things without integers. So the thing just to note is that k is your power, and your function must be of the form 1 plus x to the k. And if it isn't 1 plus, you have to make it that way, and if it isn't a 1, you've got to make it that way, so it can be a bit tricky. Okay, so let's do an example. So here we have f of x. First of all, let me pull out that 9 from the denominator so I can make it a 1 something. 9 times 1 minus x over 9. Okay, well that's the same thing as a third times 1 minus x over 9 to the negative 1/2 power. Or that's 1/3 times 1 plus negative x over 9 to the negative 1/2 power. So what we're going to use here is that k, our power, is negative 1/2. And we're going to use, instead of x, we're going to use negative x over 9. Goes in for the x. Okay, so in general, here's our formula for these. We have that f of x is equal to 1 plus kx plus k minus 1 over 2 factorial x squared, k minus 1, k minus 2 over 3 factorial x cubed, etc. That's the best way to work with this definition. So our f of x, first of all, we have that 1/3 hanging out in the front, so we'll just factor him out. Then we have 1, and plug in your k, plug in your x. So plug in negative 1/2 for k, negative x over 9 for x. Then I'm going to make that 1 over 2 factorial. K is negative 1/2, and then negative 1/2 minus 1 is negative 3/2. And we have negative x over 9 squared. And then plus 1 over 3 factorial, negative 1/2, negative 3/2, negative 5/2, and then negative x over 9 cubed. plus more stuff. So here we'll have 1 plus, and don't multiply stuff, it's easier, 2 times 9, plus 1 times 3x squared over 2 factorial, 2 squared, 9 squared. And plus 135x cubed over 3 factorial, 2 cubed, 9 cubed. And convince yourself that that last term is positive. Well, we have 3 negatives here, 3 negatives here, definitely going to be positive. Okay. Now, often with these series, you can't actually put everything into a sum. You have to leave out the first few terms, and WebAssign will help you by prompting them and leaving them off. Turns out in this one, we can make a pattern for everything except for the 1. So we're going to start our sum at, well, I think it's easy to start at n equals 1. And there's the easiest parts are the factorials. We obviously have a n factorial, a 2 to the n, and a 9 to the n. That's pretty obvious. Also obvious is the x to the n. The part that's less obvious and is legit tricky is this whole like thing that's factorial-ish. It's skipping stuff. So it's all the odd powers. Well, if you're going to do it that way, I think, so 1, 3, 5, the question is how does this 5 relate to that 3? How does that 3 relate to that 2? I guess and check it's either 1, 3, 5 up to 2n plus 1, or 1, 3, 5 up to 2n minus 1. And let's see. So when we're at x equals 3, or n equals 3, if we plug 3 into this one versus 3 into that one, into the first one we get 7, and the second we get 5. So we're going to need that second one. 1, 3, 5, up, 2n minus 1. That might not be the only way to write it, and perhaps if you begin your sum at 0, you could use 2n plus 1. That probably will work. But just do your best with those patterns. All these are a bit tricky, and we're probably not going to ask much about them other than some WebAssign questions. So this is the table of common Maclaurin series that you should know. Some of them came from the previous section, and some of them come from this section. So the first one is the 1 over 1 minus x, which came from the geometric series. I want you to list out what that looks like. It's 1 plus x squared plus x cubed, blah, blah, blah. Its radius of convergence is 1. E to the x is x to the n over n factorial, that's 1. X over 1 factorial, x squared over 2 factorial, x cubed over 3 factorial, blah, 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 blah. Radius is infinite. Sine is all the odd powers. X minus x cubed over 3 factorial, x to the 5th over 5 factorial, minus x to the 7th over 7 factorial, blah, blah, blah. Also infinite radius of convergence, which means you can plug any x into it. Cosine, all the evens, 1 minus x squared over 2 factorial, x to the 4th over 4 factorial, blah, blah, blah. Also infinite radius. Arctan, this came from section 11.9. Notice this is kind of like sine, except for there's no factorials. So x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7. No factorials at all. I almost put one there by accident. And this has radius of convergence 1. ln of 1 plus x is also section 11.9. This one's a bit funky because it begins at 1. And it's given it's x minus x squared over 2 plus x cubed over 3, etc. Its radius of convergence is 1. And the final one, the binomial one, the best way to think about that is 1 plus kx plus k minus 1 over 2 factorial x squared, etc. Its r is also 1. Now, using that table, you can actually find the sum of following certain series exactly if you recognize that it's a Maclaurin series and the number you're putting in is within the radius of convergence. So this guy looks like e to the x, which is equal to the sum n equals 0 to infinity x to the n over n factorial, with x equals 3. So this sum is equal to e to the third. You could go back and look in the ratio test section and look and see that there are some examples of this there as well. Okay, this guy, well, that 2n plus 1 factorial should give you a big fat hint that this might be sine. So first notice that this is true. Negative 1 to the n. I have pi over 3 all to the 2n plus 1. It's kind of like this was simplified and then that 3 to the 2n plus 1 was thrown in the denominator. So this is the Maclaurin series for sine with pi over 3 plugged in. And sine of pi over 3 is the y at that angle, which is root 3 over 2. These last two, let's find these exactly, but first you've got to put them into summation notation. So this is equal to a sum, n equals 0 to infinity. Obviously there's over an n factorial here. And then we have a negative 1 to the n, and then we have an ln of 2 that's also being raised to the n, which is the same thing as the sum from n equals 0 to infinity, negative ln 2 to the n over n factorial, which is, that's the Maclaurin series for e to the x at x equals negative ln of 2. So this is e to the negative ln 2, which will simplify if you remember your e rules. That's e to the natural log of 2 to the negative first. So this is just 2 to the negative first, or a half. That's a funky way to write a half. Okay, and this last one. So what we have here are 1, 3, 5, 7. And without factorials, okay, so that's some kind of 2n plus 1 pattern going on. And then we have negative 1 to the n and a 2 to the n, which is the same thing as the sum n equals 0 to infinity, negative 1 to the n. Oh, and this is actually 2 to the 2n plus 1. 1/2 to the 2n plus 1 over 2n plus 1. And if you look at that table above, the function this is arctan. And it's arctan with 1/2 plugged in. And I don't think that's one you can work out well, so just leaving it as arctan of 1/2 is good enough.